Svensk översättning av Lunchsamtal Geoengineering med stratosfäriska aerosoler från The Salata Institute, Harvard University, 10 mars 2025.
To tell you the truth, I'm scared. Scared about what's happening to our planet. 2016 was recently named the hottest year on record, making it the third consecutive year to set a temperature record. Global warming is more of a problem than it's ever been before. The more hottest years on record we have, the more we'll be threatened by things like rising sea levels and extreme weather events. But I'm sure you've heard all that before. That's old news. But as some new news, we are taking a step in the right direction. Last year in Paris, 195 nations agreed to cut their carbon emissions, showing that world leaders really do recognize the dangers associated with global warming. And I think it's great that we're taking collective action, but there is a problem. Earlier this year, the United States government indicated that they want to withdraw from the Paris Agreement. Now, the United States is the world's second largest greenhouse gas emitter. Every year, we release around 6.6 billion metric tons of CO2 equivalents into the air. That's 18 times as much as the weight of corn we produce every year. We produce a lot of corn. I know you all know that. And so continuing with these astonishing emissions rates will have long-lasting and perhaps irreversible consequences. So the question becomes, we're forced to ask ourselves, what if we do get to a point where global warming is getting out of control? With the recent climate change denial and inaction in the US government, now may be the time to address the science and morality behind new solutions to global warming. And for the past couple years, I've been studying one of these solution ideas. It's something called geoengineering, which sounds complicated, but it's really just an umbrella term for things and methods to, on a large scale, cool the climate as a response to global warming. Now, there are multiple ways you could go about doing this large-scale cooling, but the one that I've focused on is an idea called marine cloud brightening. So to explain marine cloud brightening, I'm going to give a quick crash course on clouds. Who out there has seen a cloud before? Yeah, I expected that. I mean, everyone knows what a cloud is, right? But actually, what the heck are clouds? Well, they're really just collections of many tiny water droplets and sometimes ice crystals. And when sunlight hits these water droplets, they let some of it through, but they also reflect some back up into space. And the clouds act kind of like big, soggy mirrors. And that's why stormy clouds, for example, look so dark from below. They're so thick that they're reflecting away almost all the sunlight that hits them. As you probably know from walking here today in good old Providence, when clouds block sunlight, it can get cold. So what if you could make clouds more reflective? Well, then the Earth's surface would cool down even more. And that's exactly the goal behind marine cloud brightening. You make the clouds over the oceans more reflective, which would help to lower the planet's temperature. So how do you make clouds more reflective? Well, you do that by increasing the number of those droplets in the cloud. And the proposed way of doing that would be to take these funny-looking vessels, which are actually quite amazing feats of engineering, out into the ocean, where they'd spray a fine mist of seawater into the air. As this mist rises, it would come into contact and mix with a type of low-level cloud that covers 20% of the Earth's oceans, called marine stratocumulus. And so when the salt crystals that were in this salty seawater, when they come into contact with these clouds, they become what we call cloud condensation nuclei. They actually help water condense into more droplets. These more droplets are better at reflecting sunlight, making the cloud, quote unquote, brighter. There you have it, marine cloud brightening, making clouds over the ocean more reflective. And the interesting thing is that modeling has actually shown that if you can brighten enough of these clouds, which you can with a network, theoretically, of those vessels, and for a reasonable price, you could completely counteract the warming that would be caused by doubling today's levels of CO2. Now, I've just given you a lot to chew on. Is everyone still awake? Let's take a step away from the cloud physics for a bit. Basically, I'm telling you that there's a way to hack the planet to lessen the effects of global warming. Now, some of you out there are probably like, that's an interesting idea, but I wouldn't be surprised if a lot of you were like, this guy is crazy. Building machines to control the climate sounds like a really, really bad idea. You know, I've seen the YouTube comments on the other TED geoengineering videos, and they're really not pretty. But, you know, I do get it. I mean, geoengineering seems like a counterintuitive thing to be suggesting. Why on earth would we want to meddle more with the climate? We're obviously really bad at doing that. Isn't that what got us into this mess in the first place? But let me be clear. I'm not saying we should go out right now and dump a bunch of salt water into the air. For one thing, we need to do a lot more work to assess what kind of consequences that might have. But right now, I'd like to focus less on the specifics of those physical consequences and more on whether we, as humans, have the moral right to intentionally modify the Earth's climate. The man who invented the idea of marine cloud brightening, his name is Dr. John Latham. He used to be my research supervisor, and he once told me that with this whole geoengineering thing, we're essentially playing God. And that's really not something to take lightly. I feel like the phrase playing God gets thrown around a lot nowadays in science, but people don't ever really stop to think about what that entails. You know, as humans, we have the ability to modify something as large and as complex as the Earth's climate. And with global warming already, we're starting to see unprecedented changes in weather and climate everywhere, not just limited to a specific area. With geoengineering, we're talking about making these scale of changes intentionally. So it sort of seems like we've come to the point where our actions might not just be human in scale anymore. They might be somewhere closer to godlike. And then the question becomes, how do we use this power? We're here today to talk about breaking barriers. So how do we break the barrier, or do we break the barrier between acting like mere mortals and acting like gods? And I've struggled a lot with this question. You know, at the beginning I mentioned that the idea of global warming has always scared me. But in the middle of high school, when I became introduced to this idea of geoengineering, started working with Dr. Latham and my friend Nick out there, I was like, wow, you know, this actually might be a solvable problem. You know, we can fix this. But the more I've looked at the sheer numbers of how much carbon we're emitting and the research that's out there, the less sure I've become that this is something we want to put ourselves in the position of having to do. So I don't claim to have the answer, but to help you think about it, I'll present two arguments in favor of geoengineering and one against it. The first justification for geoengineering looks something like this. We should geoengineer so we can optimize the climate for human activity. Now, I'm an engineering student, so in my limited experience, I found that the point of engineering is designing or improving something for human benefit. And so with this climate engineering thing, we can cool the planet, sure, but like, why not increase rainfall to help grow our crops or make certain regions more temperate and comfortable to live in? But while it might be tempting to turn the entire world into Palm Springs, we need to keep in mind that if we approach geoengineering with this mindset, we're implying that the Earth is just another thing that humans have the right to dominate. And while we may act like gods, we must remember that our power is bounded by our limitations, our arrogance, and the gaps in our understanding, among other things. So as a response to the last argument, here's a compelling reason not to geoengineer. We should not geoengineer because nature is complicated, it's powerful, and we've messed with it enough in the first place. Attempting geoengineering isn't worth dealing with the repercussions it would cause. So real quick, if we take a look at our track record of modifying the climate, let's see, we've caused global warming, and that's it? I know that was technically unintentional, but it just goes to show how bad we can be at predicting the consequences of our actions. And truthfully, with geoengineering, we don't yet know enough about it to actually go out and try it. But then there's the problem of politics. So say one day we do decide to go out and try geoengineering. Well, then who would be responsible for actually doing it? You know, the changes brought on by geoengineering would affect literally the entire world. And we don't have a governing body or an organization that represents the entire world's interests. A common problem that comes up when talking about this stuff is who sets the thermostat? What if one country wants the temperature here and another wants it somewhere else? Finally, the last argument for geoengineering sort of combines the previous two. Okay, so I get that we shouldn't be meddling with nature because it's probably smarter than we are, and we shouldn't be taking up the mantle of God. But don't we have the moral obligation to protect and fix the problems we've created with global warming? And this argument keeps in mind that geoengineering does have limitations. You know, it might even be the lesser of two evils, something we'd only want to do if absolutely necessary. But it also keeps in mind that as humans, we have a moral responsibility to preserve the property, the rights, the general well-being of our species. As a friend of mine once put it, what property is more common than air, and what right more fundamental than breathing free? We have the moral obligation to preserve our environment, our Earth, even if it means dealing with the consequences of geoengineering. All right, so what are these arguments saying? What do we want? Well, we want a climate that is habitable and conducive to human activity. We don't want to meddle with the climate more than we already have, but we want to create a future, we need to create a future where the well-being of humans, and therefore of the Earth we call home, is secure. If we take a look at these things that we want, the solution starts to become clearer. We need to do what we set out to do with the Paris Agreement. We need to slow down our emissions and mitigate our output of carbon. Think about it. Developing and implementing renewable energy technology will help spur the advancement of industry. You know, it'll grow our economies, give back to our societies, but it'll also help us work toward a more habitable planet, both for us and all the living things that share it. But you know, where does that leave us? I mean, we obviously have trouble following agreements like Paris, and that's what's so scary. And maybe I've even scared you a little bit today. But there is still reason to have hope, because we might not yet be at that point of no return, that point where we might need to geoengineer just to survive. And there are things everyone in this room can do to help. Turn off the lights, or at least buy a better bulb. Vote with your dollar. Plant a tree. And most importantly, get out there and shout. Encourage the people around you to take action as well. I'm not kidding. These things really do add up. I'd like to leave you with a quote by Henry David Thoreau. He says, "I love nature partly because she is not man, but a retreat from him. None of his institutions control or pervade her. In her midst I can be glad with an entire gladness. He is constraint. She is freedom to me. He makes me wish for another world. She makes me content with this. Let's preserve this nature, this earth. Let's stay on the path we've headed down with the Paris Agreement and not deviate back to our old dependencies on non-renewable resources. And I really do have confidence that together we can avoid creating a world where geoengineering is our only course of action." Thank you.
8 år senare, för en vecka sedan, låter det så här.
Maybe that's a little constrained by geopolitics. And maybe more critically, we actually get to choose how much to put into the stratosphere every year, and nobody is going to say, oh, it's 2080, and that Doug MacMartin guy, before he died, said we should be putting in 10 teragrams this year, so that's what we're going to do, entire degree Celsius, which is a pretty big intervention. So it's, you know, it's a downside. It's a known downside. It's not a showstopper, I guess I'd say.
Det som ligger bakom filmen försöker skapa bilden av att denna teknik inte redan existerar och används globalt.
I was just wondering if you had any insight on like the geopolitical tensions around this, and like if any countries are like specifically for or opposed to this, and what the process of actually negotiating this might look like.
I think that's actually a little bit of a hard question to tease out, because the answer is at the country level, I don't think there's any countries that know much about it. And I certainly don't think any of the countries know enough about it to really have an informed position. So if you asked what their position is today, given like this much knowledge, and then they suddenly had this much knowledge, their position might change. So I think it's pretty hard to predict what future geopolitics might look like based on current geopolitics in that sense.
Are there any like international leaders in this field that have kind of come up yet, or is it too early for that?
I mean, no, there's nobody who's pushing for deployment other than, you know, random armchair philosopher type people, or like making sunsets that's releasing a few balloons of microscopic amounts to the stratosphere. And I think, quite frankly, my take on making sunsets, if people aren't familiar with this, this is some Silicon Valley tech dudes, like surfer mentality. They're, but really, so they're launching balloons with like kilograms worth of stuff. And really, I think it just drives home the fact that that's not a risk. There's no way that what they're doing is remotely scalable to have any influence whatsoever on anything. That you're not going to be able to deploy this without a nation state having at least tacit support. You need runways and airplanes and supply chains and all of that. That you're not going to be able to deploy this without a nation state having at least tacit support. You need runways and airplanes and supply chains and all of that.
Dessa människor är livsfarliga och har helt förlorat kontakten med verkligheten. Man talar om tekniken som att den är för framtiden, men den används redan, och det är delvis de här operationerna vi upplever i vårt luftrum.
Sort of stuff that you only get with a nation state. Europe, I guess, is sort of tentatively suggesting, I don't think they used the word moratorium, but did they actually use that word? I can't remember what was actually in the document. A recommendation. Europe, I guess, is sort of tentatively suggesting, I don't think they used the word moratorium, but did they actually use that word? I can't remember what was actually in the document. A recommendation.
Jag tror den här videon är offentlig för att allmänheten ska tro att det är forskning som ännu inte implementerats, men även för att lura studenter att det inte är något som redan sker.
This came up at UNEP. A bunch of African countries objected to even evaluating it.
För 8 år sedan sålde man in tekniken, men man har fortfarande inte implementerat den. Vad konstigt. Tekniken som redan används förstör ozonskiktet. Det går således inte att sluta. Man har förstört jordens UV-skydd och ingen bryr sig. Svensk översättning av Lunchsamtal Geoengineering med stratosfäriska aerosoler från The Salata Institute, Harvard University, 10 mars 2025. Stötta min kanal och översättning. Swish 0735 30 95 07 eller paypal.me/Martin Stenso.
So thanks everybody for coming. I'm Josh Horton. Today we have Doug MacMartin with us. He's Associate Professor at the Sibley School of Mechanical and Aerospace Engineering at Cornell University. You've been involved in discussions about SRM for a while. I think so. You're an old hand.
Close to 20 years.
Yeah. So
I was at the NASA Ames meeting in 2006.
2006. So you've been around. You know your stuff. The talk today is going to be called, what I have down here is Geoengineering with Stratospheric Aerosols. What do we need to know? Now it's reflecting sunlight using stratospheric aerosols.
Sorry, I can retake that if you want.
No, it's all good. I'm looking off my notes. So welcome, Doug. Thanks for coming, and we will take today.
Thank you. So I will. I'll give a very brief introduction. I'll try to keep that fairly short because I'm going to assume that most people here are already fairly familiar with the subject. I can spend a little bit of time on what we already know, and I actually want to spend a little bit of time, more importantly, in a sense, on some of the things that we don't know. So just in starting on terms of terminology, this gets many names. Solar geoengineering, solar radiation modification is the IPCC term. I've taken to calling it sunlight reflection methods, just to try to use plain English, but keep that same acronym. I've often referred to it as climate engineering, primarily to stress the fact that this is engineering, right? So what is engineering? It's taking scientific principles to address a specific purpose, so not curiosity driven, but we're actually trying to solve a specific or address a particular thing. And in that sense, what we're talking about with things like putting stratospheric aerosols into the stratosphere to reflect sunlight is essentially a giant engineering problem. Okay, that slide advance. Oh, slide advance thing's not working here either. How about that? Let me try that. Just by way of context, of course, 1.5 degrees is a completely arbitrary political threshold, but we're now past that. And no signs of slowing down. And this is from the New York Times article. And the reason I put this up here is because I'm always entertained to see plots like this that say, well, you know, if we started in 2005, we'd have had to follow this emissions trajectory. 2015, we'd have to follow this one. Starting today, we'd have to follow this emissions trajectory. And it just feels to me a little bit like the classic New Yorker cartoon of then a miracle occurs, right? Like, we haven't changed our story, even though it's blindingly obvious that not only did we blow past 1.5 degrees, we're not even slowing down, and so the odds that we're going to stay below 2 degrees are pretty slim. And even those numbers on that plot, those are only for like 50-50 odds of staying below a climate target, right? And you'd never accept 50-50 odds in any other field. So the usual plot that people talk about when they introduce geoengineering or SAI or anything is this does not change the fact that we have to cut our emissions. We have to cut them to zero. Cutting our fossil fuel emissions to zero is not a solution to climate change. That's simply when we stop making things worse. What is in principle a solution to climate change would be to pull all that CO2 back out of the air. Lots of ideas in that space. Nothing that is obviously cheap and scalable without impacts. So plausible that that will occur eventually. And of course, all of these really have big uncertainty bands around them. If I told you future emissions, we don't know how much it warms. We don't know what the impacts are. We have no idea about future policy. We have no idea about future technology. And so we are sitting here somewhere. Who knows how far away we are from peak warming, but we certainly, no matter how confident you are about renewable energy or politics or anything, nobody can honestly say that we have zero risk of significant future climate damages. So that's the context, combined with the fact that we know how to cool the planet. The one method that we know for sure would cool the planet, just from observing what happens after volcanic eruptions, is if I fly an airplane to the stratosphere with sulfur dioxide and release it, I know with 100% confidence that that will cool the planet. I don't know everything else that'll happen, but I know we can cool the planet. The other idea that gets talked about a fair amount is marine cloud brightening. I'd say much less certainty, much less understanding on the physics, and much less understanding of the engineering. It is not actually, so this is a picture of ship tracks off of Europe's Atlantic coast. formed by the pollution from the ship interacting with the clouds. We know that there are conditions in which you can make clouds brighter. We know there are conditions in which putting aerosols in makes clouds less bright. We don't fully understand the boundary between those. We reasonable confidence that you could design something from a climate perspective, but not at all clear whether there is any engineering solution at all that would allow you to disperse salt aerosols in a way that would make marine cloud brightening an option. So when we're talking about geoengineering, the one thing we know for sure is plausible is the stratospheric aerosol injection. So back to this picture. The question at some level would be, is it better to do some amount of sunlight reflection in the interim or not? There are at least, well, there's a bunch of problems with this figure. One is I deliberately don't quantify these axes. This might be centuries. The climate impacts one, I drew this as a straight line. If you wanted to keep global mean temperature at some constant value and say we're just going to hold it at 1.5 degrees, you could. But not all impacts are going to be reduced the same way. That is to say, this 0.2 is cooler than 0.1, but it's not the same climate state, right? If you warm the climate with one mechanism, you cool it back down with a different mechanism, you don't get back to where you started. So understanding the climate impacts of that point are unclear. Usually what we wind up doing is we actually, in climate modeling, we compare this point to this point and say how different is that? That's not quite the policy relevant question. The third issue with this plot is it implies that the decision whether or not to do sunlight reflection is independent from the other decisions. I think it should be, in the same sense as when I get in my car in the morning, I don't make a decision about should I drive carefully or should I wear my seatbelt. I do them both. I think in most aspects of human endeavor, we're actually capable of doing more than one thing at a time. But that would actually be the assumptions about that, whether the choice to do sunlight reflection changes the future trajectory of emissions, is, I would say, probably the number one, at least implicit objection that people have when they talk about this subject. I'm going to show you one result from climate, well, I'll show you a bunch of results from climate models, but just to start off with, just as the existence proof that argues that we should be paying attention to this subject, these are simulations from WACM, CESM with the whole atmosphere climate model, community climate model. The left panel is temperature, the right is precipitation. The top row is warming under SSP 245, one particular future climate model scenario. And then the second one is taking that same warming but offsetting it, and I think this 1 degree is I think that was from a previous slide. That's not correct. If you believe these climate model results, which is a caveat, any climate impact that's driven by temperature, it's pretty hard to argue that this is riskier, known to be riskier than that. And there are lots of climate impacts that do, in fact, depend pretty much just on temperature, but not all of them. Even if you look at precipitation, shading here is stuff that's not statistically significant with 3 ensemble members of the climate model. So there are clearly places where the precipitation impact in this particular climate model are not, you might argue if you're in Northern Australia, for example, there's no statistically significant change in rainfall under the climate change alone, but there is if you do both climate change and geoengineering. So any climate impact that depends on precipitation, the story is a little bit less clear, but I think it's still broadly, if you said, would you rather live in this world or this world? If you hadn't done any other work at all, I think there's at least a reasonable argument, at a minimum, that this is less risky than that. And I think that's what you should broadly expect as your prior. So this is basically comparing points 1 to 3 and then comparing points 2 and 3.
Sorry, could I ask one clarification question?
Yeah.
This is in the annual average?
Oh, yeah, sorry. Yes, right, yes. This is the annual average, so it's burying lots of stuff. And it's only 2 variables, right? We care about way more than just temperature and precipitation.
So I was wondering, in precip, I guess you would expect like coherent shifts in the ITCZ and the jets that might show up more clearly in seasonal averages than in
Yes, yes. Although it is also true that when you go down to sub-annual scales, your signal to noise often gets even worse. In this particular climate model simulation, you basically don't see much of a signal in El Nino, and you don't see much of a signal in the Asian monsoon in this particular climate model with this particular strategy. So I wouldn't take this as, this is not a measure of impacts. This is just a sort of an existence proof that says there's enough of it, right? Like when you're starting to think about the subject, when we started looking at this 20 years ago, it's like, oh, that's an interesting idea. We'll go turn the sun down in a climate model. Oh, doesn't look so bad. Maybe we've got climate models that put SO2 into the stratosphere. Let's try that and see what happens. In a sense, this is the culmination of that phase of the research. It's, we've got climate models. We shouldn't take that as the end point. Just running a climate model we've got, that's not the end point. But it's certainly a reasonable thing to do is you run the climate model and you go, huh, actually looks not too bad. And then of course the next questions are, do we trust the climate models? And then a few other questions on top of that. Oh, hey, this is magically working again. I've been having lots of problems with my laptop because I was stupid enough to install the latest Windows update, which trashes lots and lots of computers. If you happen to have Windows and you've installed the update and it didn't trash your computer, you're probably in the majority, but it does trash a bunch of ours. I actually want to start, I'm going to say a little bit more about what we know from the modeling to date, but I do want to be clear when you're thinking about, well, we're going to weigh the question of the impacts and risks of climate change somehow against the impacts and risks of doing this. You can break this down into sort of what are the physical climate effects of, without trying to define what these words responsible and well-designed mean, of like, if you were a benevolent dictator saying, here's how I want things, here's what I think is the best way to do stuff, that's essential. This is essentially what that last plot would be, right? So you could basically say, I'm going to take these, I'm going to really understand the climate model better. I'm going to really drill down into what all the impacts are. I'm going to do a whole pile more work in this line of thinking. That line of thinking is roughly this category. I do want to be explicit. One should also pay attention to the fact that the world doesn't necessarily, politics doesn't necessarily unfold in a perfect way. You can certainly imagine somebody getting elected in some powerful country at some point when one's relying on geoengineering and just saying, this is stupid, the government shouldn't be spending money on this, I'm going to kill it. You can imagine things that are multiple countries doing this at different, with different goals and so forth. I'm not talking about the geopolitical, so there's a question of what the physical effects of those sorts category of things are. We're doing a little bit of work in this as well. I mentioned briefly this influence on mitigation. Personally, I think the literature on this doesn't necessarily suggest that that's a big risk, but it is certainly something lots of people are concerned about. That doesn't necessarily mean you shouldn't do it. And then what is, in some sense, the worst possible outcome would be there's a deployment. Not everybody agrees that there should be a deployment. There is some bad weather event in country X that eventually leads to nuclear war. Right? The worst possible things in this category are clearly worse than the things in here. I'm not a social scientist. I'm not really going to spend much time talking about these, with the caveat of saying I think one of the best ways to reduce these risks is to make sure that you have adequate scientific information that is broadly legitimate, that everybody can look at and say, okay, we agree that that we know these things, and we agree that this is our confidence and understanding, and so forth, so that you're at least starting from the same page. Okay. Imagine you're, whatever, 10 years from now, climate has gotten way, way worse, some massive climate disaster is happening or something, and you say, what do I need to know to be able to make informed decisions about whether to deploy? Obviously, what do we think is going to happen? Good and bad. How does that depend on how you do it? I haven't said much about this yet. I will. But the answers depend strongly on where you put the aerosols into the stratosphere, for example. Whether you're putting them in at high latitudes, whether you're putting them into the tropics, and so forth. So there's no, they also depend on how much you're cooling. How does that compare with not deploying? How confident are we? Or so what are the risks? How do those risks compare with not deploying? How do you improve confidence? Are there fundamental limits to how much we can improve confidence? If you were to read an IPCC, if you were to like say, I'm an IPCC, I'm going to go write a special report, this is typically the sort of stuff you would expect to see. There's an additional question about how one would deploy that I think has generally been really, really underfunded and underthought about for a couple of reasons. I'd say, first of all, if the whole reason you're doing the research is because somebody might deploy, different people, I personally, other people would disagree with this, but personally I'd say, what's the point in doing that research if at the end of it you can't deploy? You're not informing any meaningful decision. But what I would say is less arguable is understanding what the options for deployment are affect these answers up here. And so because the effects depend on how it's deployed, you have to actually spend a little bit of time thinking about how it's deployed. Uncertainty, this is not like jumping out of an airplane with a parachute and hoping it works, because you can't unjump from that airplane. But if you're ever deploying, you can learn as you go, as you're gradually ramping up, and you can use that information to adjust your strategy. And so you cannot say anything meaningful about what the risks are without thinking more carefully about that question. So I'm going to come back to that one towards the end. And then finally, I'm not a social scientist, so I'm not going to pretend to play one. I've decided that I'm just going to take all of the social science questions and lump them into one category and not pretend that I'm an expert in that. The one other thing I would add to this slide is that these questions are actually a little bit too vague. And if you read the literature on geoengineering, it is absolutely full of people doing things like cooling the planet by 4 degrees with geoengineering in a scenario where we burn all of the fossil fuels that you can possibly imagine, then taking 20 ensemble members and a 20-year average. So now I have 400 years of climate model output. And I'm taking that 400 years of climate model output with 4 degrees of cooling and saying, oh, look, it's a little different over here. Right? You can't just say, what are the effects without thinking a little bit more carefully about what's the decision you're trying to inform. So I'm going to attempt an answer here, is that the decision we're trying to inform would be whether or not to start ramping up deployment towards something like a 0.5 degree of cooling. Why did I pick a 0.5 degree? 2 reasons. One is we have an IPCC special report saying 2 degrees is distinctly different in risks from 1.5 degrees. So we know that a 0.5 degree of cooling, at least a 0.5 degree warming, has a meaningful increase in risk. The second is that we're currently warming the planet by like a 1/4 degree per decade. If you said, I don't want to cool the planet, I don't want the rate of cooling to be a whole lot more than our current rate of warming, that would say that it's at least a decade after the start of deployment before you'd be at a 0.5 degree. So in answering these questions, I think it is much more useful to anchor these questions on something like, what would the effects be if we were cooling the planet by 0.5 degree, and comparing that with what the effects would be if we did not cool the planet by 0.5 degree, rather than just sort of free-for-all, anybody making whatever comparison they feel like. When do we know it? When do we need to know it? I don't know. I would actually say the earliest I could conceivably imagine anybody deploying would be in any serious way would be 2035, so 10 years from now. From a research perspective, that is insanely tight. Maybe you think this is a super awful thing to do. You might still want to make sure the research is there before someone else considers deployment. You might also say, well, we need to make sure we have good governance in place before any of these things happen. If you want to actually have good governance in place, you still need to know a little bit about what it is that you're governing. And so you want this information for that as well. Broadly, I would say that all says we need to know stuff sooner than it's realistically plausible to know it. Okay, what do we know? Just as an observation, this was just pulling out of a paper, tropopause heights in January versus latitude. If you want to deploy in the tropics, say somewhere between 30 north and 30 south, that forces you to be up at 20 or 21 kilometers. I don't think that's fundamentally hard to design an airplane that will get to that height, but nobody's ever done it. So we don't for sure know that it can be done. But you could also do something, this is just marking off the service ceiling of large commercial aircraft. Boeing 777s, a little over 13 kilometers. Business jets can get up to about 15 kilometers. You could, in principle, use these existing aircraft to do stuff up at the high latitude regions. Your aerosol lifetime is not as long, but that doesn't really matter because if you put the aerosols in the spring, they're there in the summer when you really need them. The fact that they then fall out before the winter doesn't really matter. So when one's thinking about deployment scenarios, this is an entirely plausible nearer term deployment because of the fact that you could almost certainly do it with business jets. You could potentially even do this with like Boeing 777, in which case it wouldn't actually even require that many airplanes. Implementation, maybe I'll just skip this because I basically just said that. The only other thing I would add to this is that if you want to get a new airplane that'll go up to this high, the engine technology you need to do that is tightly controlled. Right? There's only a handful of engine manufacturers on the planet. All of those have Defense Department connections with their home countries. You are not going to be able to do this without the political support, at least behind the scenes, of a superpower. The end. The idea that a rich person could do this by themselves is nonsense. The idea that a country like Philippines could do this by itself is nonsense. Quite frankly, India couldn't do that because they don't have engines. The airframe's easy. Okay, so we know that. I already showed you this plot that basically says we know it would cool. We know that it reduces things like heat extremes. Sea level rise, the thermosteric is easy. We know the sign of that. The Antarctic story, in terms of loss of sea ice there, is a little less clear. I mentioned that already. I said that already. Ozone, this is just simulations in Wacom starting in 2035 to hold temperatures at 2030 levels. Over Antarctic, that will reduce ozone level. It'll slow the recovery and bring ozone levels all the way back to today's levels in Wacom. In the tropics, well, actually in the mid-latitudes and tropics, the effect is broadly comparable in magnitude to the effect of the 11-year solar cycle. And in the northern high latitudes, it actually tends to result in the model in a net increase in ozone, if the model's right. What's actually happening here is two competing effects of opposite sign. You're speeding up the Brewer-Dobson circulation. You're transporting more ozone to high latitudes because you're speeding up that circulation, and you're destroying more ozone at high latitudes. And then there's additional chemistry, NOx chemistry in the tropics. There are people in this room who know way more about stratospheric chemistry than I ever will. But just to say, if you believed the model, there's a big if there, you would say that's not necessarily a reason not to do it. The question then, of course, would be how do you validate that the model is actually correct? Deposition, this is a map of present-day deposition. This is on the same color scale. The additional deposition, if you were cooling the planet by 4 degrees Celsius, which is an insane amount. If you rescaled this to a ½ degree Celsius, you'd see that there are some areas that are currently pristine, that is to say they don't have a lot of industrial pollution, that would see some notable impacts. But by and large, acid rain, the amounts that we're talking about are relatively small compared to our current industrial pollution. And it comes down more distributed, so a lot of it comes down over the ocean, where it doesn't matter. Sorry?
What would be the deposition?
Sorry, if you're putting sulfate in the stratosphere, it comes down as acid rain.
What would be the value relative to this?
Right now, so to cool the planet by a degree of cooling is order 10 teragrams of SO2. 5 teragrams of sulfur, whatever that is, 15 teragrams of sulfate. So it's of order 1/7 of our current pollution would be enough to reduce temperatures by an entire degree Celsius, which is a pretty big intervention. So it's, you know, it's a downside. It's a known downside. It's not a showstopper, I guess I'd say. We know that if you're relying on it and you terminate, temperatures go back up over the next decade or so. No big surprise. That gives you a year or two to react. So I guess I said all of this. The hard part is probably this item right here. Research to date, I'd say, is still mostly developed world. It's mostly been, hey, I've got a climate model, I'll run it and I'll see what happens, which is a good start. Mostly curiosity driven rather than mission driven. That is to say, mostly it's, I'm interested in this question, rather than taking a step back and saying, okay, what are the most important things to do? I'm going to switch gears a little bit and talk more about I want to get to a bit more about where we need to go. I do want to really drive home this point that, you know, this is an engineering challenge in the sense that when we do the research, there's two really critical things, right? We get to choose where to put the aerosols in the stratosphere. Maybe that's a little constrained by geopolitics. And maybe more critically, we actually get to choose how much to put into the stratosphere every year. And nobody is going to say, oh, it's 2080, and that Doug MacMartin guy, before he died, said we should be putting in 10 teragrams this year, so that's what we're going to do, right? You're always going to be, you'll see what's happening. You'll know what's happening, to some extent, and you'll revisit that choice. So this first one is critical to thinking about trade-offs and scenarios. The second one is critical to thinking about uncertainty. And of course, it's also different from climate change in that research is urgent and there's some really challenging geopolitics. I'm going to try to go through the next slides really quickly just to give you an idea of the impact of where you inject. This is 4 different simulations, all maintaining the exact same amount of cooling, putting it in either at the equator, 15 north and south equally distributed, 30 north and south equally distributed, or a 60 north and south lower altitude something you could do with more or less existing airplanes in the spring in each hemisphere, just to say where the aerosols wind up is very different. That has huge effects on the stratospheric circulation. It has, and it affects where the cooling is. This overcools the tropics, changes meridional temperature gradients, changes storms and so forth because of that. This actually has the opposite. It overcools at the high latitudes. If you're mostly worried about high latitude impacts, this is a more efficient way of cooling. And then somewhere in here is probably a sweet spot in terms of not messing meridional temperature gradients. I'm going to skip that. That's just pointing out that if you wanted to control if you wanted to manage Arctic sea ice, no geoengineering, with geoengineering, like big surprise, you can do it. Antarctic depends a lot on the strategy. The reason I put this in is just to say this line here is comparing global mean temperature versus ocean shelf temperature in a climate model. Caveats as usual. As you get warmer, the shelf temperature gets warmer. If you cool with geoengineering, depending on the strategy, you do reduce the risks on the ocean shelf. You don't necessarily get back to where you were. And then this is just two different strategies saying, depending on the strategy, if you were worried about the Antarctic ice shelf, different strategies will have a different impact on that. AMOC, Atlantic Meridional Overturning Circulation. I'm not going to, once again, sound like a broken record, I'm not going to pretend that this model is correct in its representation, but by and large, if you inject in the southern hemisphere, that's what all of these ones are. It doesn't do anything. You inject in the northern hemisphere, you can stabilize AMOC. So if you're worried about that, at least a plausibility argument that this would help. I don't want to talk too much about the uncoordinated deployment scenarios other than to write one down for fun. We've simulated this, and we have an emulator trained on climate model data, so if you wanted to do a different scenario, we could. This is just writing something down saying, okay, it's 2035, one group deploys in the Arctic. Another group decides to deploy at the equator, different climate goal to a different target. A third country decides, oh, these guys are going in the northern hemisphere. Putting it in the northern hemisphere is bad. That's going to shift ITCZ. We'll go put something in the southern hemisphere. And then, whoops, somewhere along the lines, there's going to be a termination shock. I can't tell you what the odds of this sort of thing are. I do know that people have thrown rocks at us saying what you're simulating is way too optimistic about international geopolitics. But you can use climate modeling and say, well, what are the risks of this as well? And broadly speaking, I would say you run the climate model simulation of something like this. Broadly speaking, as long as you're not doing a sudden termination, like that, or a sustained asymmetry in your deployment, just because it's uncoordinated and there's multiple actors doesn't necessarily mean it's terrible. I'm going to skip the movie of that. Mainly because I want to get back into the second question. Because I think this is where the research needs to go. I feel like we've done this bit where it's like, huh, this is interesting, we'll go run climate models. And it's easy to go to people and say, you don't have to worry about a slippery slope, we're just running climate models. I think it's important to actually start taking what deployment looks like more seriously, saying, well, what would you actually want to do? The first thing you'd do would be some experiment. You fly one airplane, somewhere in that size range, enough so that you can track the aerosols and say, is the aerosol size distribution match our models? If it doesn't, you then say, huh, let's go back and improve our models, and then maybe we'll go do this again. If it does, then you have a choice. You can still stop, but maybe you ramp up to sort of saying, okay, we're going to have a handful of airplanes just doing stuff throughout an entire season or an entire year, we'll get to make sure that we understand where the aerosols are going. I have not done the math to say at what point you'd be able to detect whether your influence on ozone, for example, is correctly modeled. This is still way too small to have an effect on climate. Right? So does the model match, does what you see match the model? If not, you should probably stop and reconsider. If yes, maybe you start ramping up. And even here, right? Like, okay, somebody's worried about the Asian monsoon. Well, okay, well, why are we worried? Because in this climate model it says there's no effect. In this climate model there is. Why do these models say different things? What's the source of that physical influence? What am I going to measure in deployment to tell me which model is right, which model is wrong, and which path I'm on? And in principle, use that information to adjust your strategy. So that's why I'd say you can't seriously talk about what the impacts and the uncertainty are without thinking about all of this. I'll only put this up for the quote. This was way back in 2007. How can you engineer a system whose behavior you don't understand? Me as an engineer is like, what? That's how we do stuff. Like, why do you think airplanes can fly? How do you manage to drive? How do you manage to set the temperature in your shower in the morning? All of these things, we do that with feedback. So this is not fundamentally different. So I'll skip the rest of that. I do want to do one, where am I in time? Okay, sorry. I'll try to wrap up with one more slide here. When one is thinking about, okay, how do we think about uncertainties and risks? Any uncertainty or source of uncertainty you can think of on two axes, and the font size is too small for you to read here. How big is that uncertainty? What's the risk of something happening? And what are the consequences of that? It's sort of that intersection that defines risk. Stuff that's up in this corner is the stuff that you really, really need to worry about. I would actually say we have not, as a field, like so a few of us tried. This is part of a new organization, Reflective, that I'm chairing the scientific advisory board with. Your former colleague David Keith is also on the board with me. We made an attempt, but a lot of this is just like, a bit of guesswork because we don't have the data. We don't have any real basis for saying how uncertain are any of these things, or for that matter, what the impacts are. We basically constrained ourselves to say, small new organization, we're just going to pick 3 things to focus on. But I think it's interesting that after all the discussion, after about 3 days, the things we landed on as things that have not been addressed in the community particularly well, but are critical to making decisions, are questions. I shouldn't really say how to loft and disperse, but how hard is it to loft and disperse? If that's a lot harder than we think, this might not even be an option, in which case, why are we doing the research? Or for that matter, if it's a lot easier than we think, that actually might feed back into governance conversations. If you were going to do this, how do you observe it? What's the actual plan? What observations do you need? Because that's potentially long pole in the tent, right? It takes a long time to develop new observation networks. You presumably want some amount of observations prior to actually doing anything so that you know what the background conditions are supposed to be. The fact that we have no idea of what plan for observations would be when you start this thing is a pretty serious gap. And I will point out that the stratospheric observations that are currently being done are with platforms that are older than I am. Wake Smith had a great comment of these platforms are older than I am, so you might ask the same question about me of how come they're not retired already. And then the third one, in thinking about what are the physical uncertainties that we really don't know, comes down to the fact that we calibrate our models to some extent on our aerosol processes and what happens after a volcanic eruption. And a volcanic eruption is not the same thing as taking an airplane with a length scale of tens of meters and flying it up into the stratosphere and releasing stuff. When we run a climate model, we just stick SO2 into a grid box that's 100 kilometers on a side. Whatever degree of spatial inhomogeneity you get within a grid box has profound implications for the extent to which you get new particle formation versus just, I get a new molecule of SO4 and it gloms onto an existing aerosol. So trying to understand the influence of that small scale physics, that to my mind is likely to require an experiment. So how do you resolve that? Is you resolve that by doing, sorry, go back one more. You resolve that by doing this experiment and basically understand your aerosol microphysics. So those are the three that we picked as our top ones. I am sure everybody in this room could say, no. This is what I think is the top one. Because I think one could generate a long list and potentially say the fact that we don't even know where some of these things are might push them up into that quadrant until we have more work. But just as an indication of where I think the community as a whole needs to go. Let me skip that in the interest of time. Broadly, I would say I don't know how much the planet's going to warm. Nobody knows how much the planet's going to warm. It could be bad. Maybe it'll be fine. Maybe it won't be. I think we need to understand what our options are. I think we should do the research now before we're facing hard choices. I would say when I first started working on this, I gave a talk in like 2008, I think it was, in Boulder, and a bunch of NOAA people showed up. And I said, the next thing I'm going to work on is geoengineering, and I didn't get to my conclusion slide because I basically got yelled out of the room. The first paper I ever wrote on this, basically, I got a review that said, we should never be deploying this, therefore we don't need research papers on it. The end. Reject. But this is not helpful. Now I would say virtually everybody that I talk to, there's a small but extremely vocal minority, but almost everybody I talk to agrees that we should do the research. Money is still tiny in the grand scheme of things. And then I'd still say, if you ask me to guess right now, I would guess that a well-intentioned deployment, gradually ramped up with a conscientious plan for how you're going to monitor it, is extremely likely to be less risky for the planet than not deploying it. I think that is basically what we know from the research to date, is that that's very likely to be where things end. I don't think we have a good enough basis to actually like write all of that stuff down. We haven't drilled down into all of the pieces. I couldn't write an IPCC report for you that everybody in the country everybody in the world would look at and say, yep, I agree with that conclusion. But I think that's where we're likely to get. That still doesn't make it easy to decide how to do it. Okay, sorry, it's 12:45. I'll shut up now.
Good. Thank you, Doug. Very much.
There's always so much to say.
Questions and comments from anybody?
I covered a huge range of stuff.
Raise your hand. Sure.
My name is Grace from HKS. Before the implementation, do you have any idea that where can we have the field experiment in your mind?
A field experiment like taking one airplane and flying it up and releasing 10 tons or something. I think we actually need, in some sense there's a premature step. I think that's likely to be something that we need. I think we should model that. I think we should actually understand, if we put in uncertainties and mixing and so forth, how important really is that uncertainty to resolve? Right? So I think before you go say, we need to do an experiment, you need to be very clear about why this particular uncertainty is limiting our ability to make intelligent decisions in this space. The only way to resolve the uncertainty is to do this experiment. This is sort of the lowest risk experiment that will answer that question. Here's our experiment plan. I think you have to present that case clearly. The honest answer would be, We have had a couple of experiments proposed. There are things that you can point at and how those experiments were presented and conducted that I would be hesitant to learn very much from them at all. So I honestly don't know how difficult it will be to get societal license, if you will, to conduct that experiment. And I think there's genuine questions, right? You can't give 8 billion people veto power over whether to conduct an experiment. But who does get to have a say in it, I think, is a genuine question. So that's not quite an answer to your question. If you're doing it with existing aircraft, you're pretty much constrained to be at high latitude because you need to be somewhere where the tropopause is lower. So you'd be really testing what happens at, say, 60 North or something. So flying out of, Fairbanks or Anchorage or something like that, or Kangerlussuaq.
Yeah, could you say a little bit more about the state of the art of our understanding of the aerosol microphysics? I mean, coagulation is such a non-linear function of concentration, and the concentration should be varying by orders of magnitude during deployment, right?
There is an aerosol microphysical model that's buried into climate model simulations. Slightly different in different climate models. Those all have adjustable free parameters. So saying we're assuming it's uniformly mixed in a grid cell isn't really quite true. What we really do is, there's some free parameters in there, and we tweak those parameters so that we roughly match what happens after observations from Pinatubo. So that we can get, but we've got limited, we've got good estimates of aerosol optical depth after Pinatubo. We don't necessarily have, we don't even know how much SO2 was released by Pinatubo super accurately. So that isn't, the volcanic observations aren't necessarily quite sufficient to constrain the microphysical parameterization that's in the model. So there is something, but we know the pieces of the physics, right? But I don't know if you, so the conversion from, if you're taking a gaseous precursor like SO2 or H2S, the oxidation time scale is weeks. It's not instantaneous. And so question in some sense would be how mixed out is that by the time, when you have a new molecule of SO3 forming, is it still forming in a really dense, high concentration area, or is it in a much more uniform concentration area? So I can tell you what a climate model does, but then you should take that with a grain of salt. I'd say, it's certainly plausible that the aerosol microphysics is radically wrong, which is why we put that one in the top right of the diagram. And we can certainly do more modeling on that, but I think that's why I would say I think it's likely that we would need an experiment on that, because if we're really, really wrong, it'd be good to know it.
So back here.
For many developing countries or underdeveloped countries, in my opinion, the total annual rainfall is important. Like in your talk, you did mention that in spite of the climate change in Australia, the total amount of rainfall has not been significantly changed. That's what I heard. Anyway, for countries like India, where I came from, in the last 60 years, I have seen the rainfall being surplus or deficient. So in the last 60 years, I'm talking about. So now, such countries, do you think that, from what I have seen in the newspapers, they hardly pay any attention to climate change? So their worry is just meeting the basic necessities of life day to day. So in your opinion, during this climate change, the total amount of rainfall, was there any change, like increase or decrease or the same?
Globally, it should go up. But if you look at a very, very specific region, I don't know. But I would also say, right, like if one's looking and saying, oh, this particular climate model simulation of SAI reduces, again, you know, global mean rainfall is not quite the right metric, right? If you're monsoon, you care about timing, you care about predictability, you care about year-to-year variability. In some sense, what you care about is what's the probability of a monsoon failure is probably the most important single number to look at. But of course, one has to keep that in the context of if the monsoon has gradually been strengthening under climate change, having it weaken because of SAI is not necessarily a bad thing. And when we generate plots, what we will typically do is we'll say, we're going to compare it to what the climate model said the climate was in 2020 and look at the differences and say, oh, look, it's a little bit different from 2020. But if the right way to think about it might be, if you bring global mean temperatures back to 2030 levels, then you bring the Indian monsoon back to 2020 levels. In which case you'd go like, okay. Right, so I think there's an awful lot, there's more physics to be understood. But there's also a little bit better contextualization that's valuable in that. I do think, you know, there are people in the developing world who are paying a bit of attention to this. I'd say there's broadly two competing narratives, and I think it depends a lot on who talks to them. One of the narratives would be, you know, you guys in the North, you guys have lots of money, you can adapt to climate change, it's not really affecting you. We live and die by it. If there's a technology that can help improve our lives, we want to know about it, get out of the way. And we've been screwed by the global North for centuries. Here's yet another opportunity for the global North to screw us by not taking responsibility for climate change. So you see both of those, depending on who you talk to. Lots of questions.
Yeah, you mentioned, you touched on the observational and like measurement abilities that we have right now. What is the gap between what we would need in terms of satellites, you know, ground measurements, all of that, and what we currently have in terms of measuring the effects?
The fact that I don't know the answer to that question is the problem. Right? Nobody has ever said, "Oh, this is exactly what we will need." I mean, I think it's fair. You know, it's fair to say the things that you want to know at a minimum are, you want to know aerosol size distribution, you want to know the aerosol spatial distribution, you want to know chemistry, so you need to be able to measure trace gases, and of course, MLS isn't going to be around forever. The aerosol size distribution you're going to get in situ. You're not going to get that from a satellite. But, you know, if you can fly a pile of airplanes up there to release stuff, you know, I guess what I'd say, you know, a really, really big picture view would be, if you're going to spend $10 billion a year deploying, you can afford to spend $1 billion a year on an observational network, and that's going to get you lots of stuff. The issue, in some sense, is what's the lead time on that? But the answer at some level is, you know, what's the very first thing I want? If I'm going to go conduct that experiment, I want to be able to find the plume for the next, I want to be able to track where that plume is for the next month. And I want it with enough accuracy that I can fly Sabre or something into the plume and collect all of the data on size distribution and stuff. As long as we still have Sabre, part of that problem is solved. But, you know, that's an old airplane, and so anyway, I talked with, you know, Jim and Frank probably have stronger opinions about this than I do. I'm sort of one of these people, like I actually came into this originally as an aerospace engineer, and all along the way it's like, oh crap, I need to learn something about this. Oh crap, I need to learn something about that. So now I'm looking at it going, huh, I need to understand what observations we need way better than I currently understand them. I'm not an observationalist.
Great. So you mentioned it's actually quite common the modern communities taking the Pinatubo as a benchmark to validate the aerosol microphysics in the models. But we know like Pinatubo is probably not the ideal case like for the solar geo, because it's inject massive amount of aerosol at the same time, at one time.
Should give you a high signal to noise.
Matters, right? So I'm actually wondering, now like we actually get more and more like in situ data about these smaller or moderate volcanic eruptions. I'm wondering how much effort the modeling community is putting to use those in situ measurement data, or like...
Yep. I mentioned Pinatubo, but yes, every single eruption that goes off, somebody on every single climate modeling center that has a interactive stratospheric aerosol module, every single one of them will say, oh, I'm going to go model this and write a paper about it.
So, like, in terms of this smaller one, like, how good the model perform, like, with that? Like, Pinatubo, I guess a lot of models probably get a decent job, but...
Is it good enough job?
Well,
I think I would defer to other people in this room on that question. Like Jim or Frank, or...
I saw a hand over there. You first, and then we'll come back to you.
Yeah. Most of the research so far in SAI has been conducted in this country, or at least a significant amount. Has any of what has happened in this country recently in terms of politics and the attacks on climate science, has that changed either your perspective on what should happen or what will happen?
Yes, in a couple of regards. I don't yet know what the fallout from the cuts at NOAA will be, but if you asked me 6 months ago, my answer would be, oh, great. The whole observational side, NOAA's got that under control. And now that's much less obvious whether that's going to still be true. I think, emissions are going to go up. So climate, my personal estimate of how much climate damage there's going to be without SAI probably went up. On a more personal thing, I know I have an NSF award that my program manager recommended for funding about a month. He said, oh, I'm going to recommend your proposal for funding. No idea. I haven't had the courage to email him because I'm sure he's got bigger challenges than hearing from me to say, hey, what's the status of that? So, yes, it'll impact funding. Right now, most of our funding actually comes from a British philanthropy.
Is that Siemens?
No, QCF. So, Simons didn't fund any of our work. They're also US. No question back there?
Hi, I'm Sejal. I'm from the Public Health School. I was just wondering if you had any insight on like the geopolitical tensions around this, and like if any countries are like specifically for or opposed to this, and what the process of actually negotiating this might look like.
I think that's actually a little bit of a hard question to tease out, because the answer is at the country level, I don't think there's any countries that know much about it. And I certainly don't think any of the countries know enough about it to really have an informed position. So if you asked what their position is today, given like this much knowledge, and then they suddenly had this much knowledge, their position might change. So I think it's pretty hard to predict what future geopolitics might look like based on current geopolitics in that sense.
Are there any like international leaders in this field that have kind of come up yet, or is it too early for that?
I mean, basically there's nobody who's pushing for deployment other than, random armchair philosopher type people, or like making sunsets that's releasing a few balloons of microscopic amounts to the stratosphere. And I think, quite frankly, my take on making sunsets, if people aren't familiar with this, this is some Silicon Valley tech dudes, like surfer mentality. They're, but really, so they're launching balloons with like kilograms worth of stuff. And really, I think it just drives home the fact that that's not a risk. There's no way that what they're doing is remotely scalable to have any influence whatsoever on anything. that you're not going to be able to deploy this without a nation state having at least tacit support. You need runways and airplanes and supply chains and all of that sort of stuff that you only get with a nation state. Europe, I guess, is sort of tentatively suggesting, I don't think they used the word moratorium, but did they actually use that word? I can't remember what was actually in the document. A recommendation. This came up at UNEP. A bunch of African countries objected to even evaluating it. It is nominally in the draft as a chapter in the next IPCC AR7. But actually that had a fair amount of argument on it too. There's a question over here somewhere.
Your last question.
Okay. You guys can arm wrestle. Let's see.
So how would you compare this to the carbon capture methods? Is it the most plausible way to do the cooling? Or?
I would say it is way faster. Like if you wanted to cut the temperature by a degree in 20 years, I don't think it's not hard. It's vastly cheaper. If you wanted to cut the temperature by a degree in 20 years, you know, it's somewhere measured in whether it's billions or tens of billions of dollars. It's not a big number. Whereas you put tens of billions into carbon capture, you're going to, you know, release this much CO2. The downside is it's as soon as you stop, you're done. So you have to keep doing it. Whereas carbon capture is actually solving the problem. So I'd say they're different, very different knobs. This is more short-term. Carbon capture is more long-term. But sometimes you need both, right? So no analogy is perfect, but at some level, I'd say if you're in a car and you know you're going to get into a car accident, you should take the foot off the gas, right? That's basically like stopping emitting, but don't assume that that's going to solve the problem. You should hit the brakes. That actually solves the problem in a sense, and that's more like the carbon capture, but you still want like your seat belts and airbags and stuff. So and it's not quite of a perfect analogy, but right, the answer is that we shouldn't be choosing between them. We should be doing yes and evaluating each one on its merits. There's no carbon capture solution that's going to measurably cool the temperature of the planet in the next 20 or 30 years.
So if you had to achieve that 0.5 degrees with planting trees, it would be completely unreasonable.
Yeah. Well, you're never going to. I mean, we didn't create the carbon problem by cutting trees down. We created part of it by cutting trees down. The part of climate change that you can solve by planting trees is roughly comparable to the part that you caused by cutting the trees, except we're now using a lot of that land. Right? So we mostly caused the problem by pulling fossil fuel out of the lithosphere and sticking it in the atmosphere. So planting trees is a good thing, but don't expect it to solve the climate problem. And dollar per degree cooling, probably a little hard to measure, but I would bet that it's the scariest approach in a sense, but it's also the highest leverage.
All right, applause.
Tack för att du tittade. Stötta kanalen. Swish 0735 30 95 07 eller paypal.me/Martin Stensö. Det går också bra att bli månadsgivare på patreon.com/Martin Stensö.